at what we've got. Or our bell work here. So we said we're working with the same PDF that we generated yesterday. This is like the number of heads that we get from 4 coin flips. So the likelihood of getting 0 heads was 1 in 16. Getting 1 heads was 4 in 16. Getting 2, 6 in 16. Getting 3, 4 in 16. And getting 4, also 1 in 16. Okay, how do we find the mean? How do we find expected value here? Yeah, this is going to be the sum of our, exactly, the sum of our essentially weighted averages, right? So this is going to be 0 times 1 over 16 plus 1 times 4 over 16, 2 times 6 over 16, 3 times 4, and then 4 times 1 over 16. What do we get when we do this? Got 2. Seems good. Does that make sense? If I'm flipping 4 coins, does it make sense that my expected number of heads would be 2? Yeah, that is exactly what we would expect to see. All right. Cool. What did I have to do in order to figure out the variance here? Okay, so we have to first do the expected value for x squared. You can leave out 0. I include it just so that we can like see that is there. But you certainly could leave out the 0 squared. So 0 squared times 1 over 16, which absolutely correct is redundant, plus the 1 times 4, 16, 1 squared, plus 2 squared times 6 over 16, 3 squared times 4, 4 squared times 1. And what do we get from this? 5. Seems good. And so what do I have to do? Sorry, forgot this. This is my expected value of x squared. Is that my variance? No. What does this mean on its own? Did this have meaning on its own? Not really. Maybe it does. I don't know what it is. We're not going to worry about it. That's more just like an algebraic construct, the fact that that exists. And so what do I have to do with this to turn it into my variance? Subtract it by 2 squared. So my variance that I get is 1. And what do I have to do to both sides to find the standard deviation? Square root of the variance, which is just 1. Yep. So this was our mean, and this was our standard deviation. All right, this example that we are seeing with the tossing coins a certain number of times, this falls under a category of what we might describe as a Bernoulli distribution, or as we are going to talk about it, the binomial distribution. So this process that we are looking at falls under a particular categorization, which we are going to be kind of expanding on and exploring a little bit today. Okay, so first and foremost, what is a binomial experiment? What qualifies what we are seeing here to be binomial? Well, first and foremost, the reason why this is kind of, or one of the reasons why this is going to be very prominent with our coin flipping examples is these experiments are going to be ones where each trial that we are looking at can only have two outcomes. Or actually better than that, because it's possible that we could see more than one outcomes. We can only have two values for our random variable, right? So think of this case as our heads versus tails. Or we'll look at an example later with dice, getting a 4 or not getting a 4, getting an even number, getting an odd number, where we only have two categories that we are looking at. Generally speaking, we divide these categories into success and failure. Yeah, this is 5.3. Another key aspect of why we can talk about our coin flips in terms of being a binomial experiment is because there are only a finite number of coin flips that we are looking at. If I wanted to toss an infinite number of coins and look at the probability of seeing a particular result, we couldn't talk about that, right? That would not be something that we could necessarily approach. So the fact that we limited our bell work to only looking at what happens when we toss 4 coins is what is allowing us to do a lot of the work that we are doing here. Also important in terms of what we are looking at here is that the probabilities of seeing a success don't change. So the probability of success is fixed. And to that end, if the probability isn't allowed to change, if it must be the same likelihood across the board, then these must be, rather, the trials must be independent. What did it mean for two events to be independent from one another? Not that they're the same. Mutually exclusive was its own thing. So what did independent mean? Event A is independent from event B. What does that mean?
In order for B to happen, event A must also happen.
No. Say again? So if event A happens, what happens to the likelihood of event B? Doesn't change. Right? In other words, tossing my coin first doesn't affect the likelihood that my second toss is going to be heads, right? First getting tails doesn't make it more or less likely for me to get tails the second time. Getting 3 tails in a row doesn't make it more or less likely for me to get tails the fourth toss, right? Every single probability is independent of one another. One happening first does not affect the likelihood of what the second outcome could possibly be. Okay, so obviously our coin toss is a pretty good example. We could think about like even versus odd for like our die. We'll see some examples of die as well, where it works out as well. What else could we see? Where there are only 2 options for outcomes here. What are other examples of events where it's either going to be A or it's going to be B? Yeah. Talk about whether it's going to be a boy or a girl. What else? What did we look at with the raffle ticket example yesterday? What were our options there? Winning or losing? So it could either be a win or a loss. If we're talking about like a lottery. Lots of different ways to do this, right? A lot of events that happen day to day are functionally coin tosses. They might be weighted coin tosses, but they are effectively coin tosses. All right. So when we have a binomial experiment, oftentimes what we want to talk about in conjunction with it is the binomial distribution. You can just think of the binomial distribution as being the PDF that goes with a particular binomial experiment. We examined this idea yesterday for our bell work, which is the idea of if I have a binomial experiment. So for instance, if I'm flipping 4 coins, right? And maybe we want to know the probability that 2 of them are heads. We have heads, heads, we could have tails, tails. What was our approach to determining this likelihood? What did we do? So there was something to do with the factorial. So we had like the number of ways we could get 2 heads and 2 tails. What did that look like? How many ways can I take this result and shuffle it?
In that order?
No, it doesn't have to be in that order. So in any order. It ended up being 6, which came from like 4 factorial over 2 factorial, 2 factorial, which is like the number of ways I can get 2 heads. And then what else would I need to do in order to calculate the likelihood of getting heads, heads, tails, tails? What's the likelihood of getting this first heads? 50%, 0.5. Okay. What's the likelihood of getting the second heads? Also 0.5. What's the likelihood of getting this tails? 0.5. What's the likelihood of getting this tails? 0.5. If I want to know the probability of getting heads and then tails and then tails, what should I do with my probabilities? Multiply all of them together, which works because my coin flips are what? Independent of one another. So this only really works because they're independent, but absolutely correct that we can take our 4 factorial divided by 2 factorial, 2 factorial. We said we have 0.5 happening twice because of the number of heads that we got, which we could think of maybe as like a success if we're measuring the number of heads. And then we have another 0.5, which happens twice, which we could think of as the number of tails, or maybe the number of failures. And this model that we see that we derived yesterday is one that's going to be very, very adaptable. We're going to be able to take it and generalize it to use regardless of what the probabilities are. We could do this if it was like a weighted coin, or we could do this if one event was incredibly likely or incredibly unlikely, something that's very, very adaptable. Now, as far as the notation that we are going to see here, we're going to denote the likelihood that our event does happen, that we get a success with P. So P is the probability of success. If I know the probability of success, how could I get the probability of failure? If I know I'm succeeding, let's say 30% of the time, how could I get the likelihood that I fail? 1 minus that probability of success. You'll often also see this denoted as Q, but you'll mostly see me write this as 1 minus P, which is the probability of failure. Okay, where did the 4 from the 4 factorial come from? Why is this 4? Yeah, we're flipping a coin 4 times, so maybe we denote n as being the number of trials, like the number of flips or the number of people that were taking, or whatever that is. And then where did this 2 come from? So how many of failures and success? We could define failures. Failures isn't, number of failures isn't too hard to define, but if R is the number of successes, how could I find the number of failures? What's number of failures going to look like? So if n is my total number of trials and R is my number of successes, how many times did I fail? N minus R will be our number of failures. Okay, I'm altering the notation ever so slightly just because it's more correct. So rather than finding exactly X successes, we're going to find exactly R successes. It just fits the notation that I use a little bit better. So in particular here, we are looking for the probability that our random variable is equal to R, that we succeed R times. Okay. Well, first of all, how many successes are we seeing out of how many trials? Well, we said we had n total trials, and we want to choose our successes. This is, again, think of this as like the number of ways to succeed. To succeed, in particular, R times. What is the likelihood of each success? What do we define that as? P. How many times is P going to happen? How often are we succeeding? For our generic example, we're succeeding. So n is the total number of trials. So number of successes is R. So if we are succeeding R times, then taking the likelihood of success, multiplying it by itself that many times. And then if we're not succeeding, then we're failing. So 1 minus P, which is the same as our Q here. And how many times are we going to fail? For our generic example. If we succeed R times, then we're going to fail n minus R times. Which is, notice, exactly what we looked at yesterday. Right? It's exactly the same thing that we saw yesterday. We have the number of ways that we can shuffle the trials that we are looking at, right? Number of ways that we can get a particular result. We look at the likelihood of getting this many successes, taking the probability of success, raising it to that power, and then the likelihood of getting that many failures, probability of failure, raising to a particular power. And then we're good to go. Okay, let's take a look at an example here. We'll do another coin toss example, but this one's going to be worse than yesterday in that it's going to be a lot harder to kind of brute force the sample space. In this case, rather than tossing a coin 4 times, we are tossing a coin 9 times, and we want to know the likelihood of seeing 4 heads. So this is the probability that our random variable is equal to 4, where we maybe define a success as getting a head, right? As having a trial be heads. The number of successes, which we are saying is synonymous with heads. Okay, so how many ways from 9 tosses am I going to be able to get 4 heads? What is that going to look like? How many coins are being tossed? 9, and I want how many to be heads? 4, so that's going to be 9. 9 choose 4. Which 9 factorial over 4 factorial, 5 factorial? Okay. What is the likelihood that I succeed? 0.5. We're succeeding half of the time. So likelihood of success, 0.5. How many times do I succeed? 4. So that 0.5 chance needs to happen 4 times overall. And then what is my likelihood of failure? 50%, also 0.5. And then if I'm succeeding 4 times, how many times am I going to fail? Failing 5 times. Plugging this into our calculator, we get that this works out to be 0.246. There's a little bit worse than a 25% chance that this occurs. Questions with our binomial definitions? All right, take a stab at this second example here, so the visiting a doctor example. In particular, focus on what is our probability of success? What does it mean to succeed? And then what is our probability of failure going to be here? I think what is a success? What is a failure? What is the likelihood of that? And then using that to compute the likelihood that we pick 3 out of 10 people who have in fact visited. And then how many failures would you expect? Well, what's the likelihood of failure? So that was success. So failure would be. Yeah. And then how many times do we expect that to happen? We have 3 successes. How many failures? We have 3 successes from a random selection of 10. Perfect.
So
Yes.
I'm gonna 10 CG.
So that's like the number of ways that we can pick 3 people out of 10. Yeah. And then it's just a matter of what does it mean to get a success? What's the likelihood of that? And then what does it mean to get a failure?
I really am tired.
Yeah, so this is like number of ways to get the 3 people out of the 10. So then what does it mean to get a success? What does a successful trial look like?
I would say 50%, but it's 1 in 5.
Okay, so 1 in 5 people are going to be quote unquote successful. Rare than. That's a little bit arbitrary there. So that's your key.
So you just figure out 1 in 5.
Well, you can use that if you want to. That's already a probability, right?
Mhm.
And then you just need to figure out if that's the likelihood of success, what then is the likelihood of failure, and then how many successes do we have? How many successes do we have? And then how many failures do we have? And what is the probability of it?
Simply choose
Is it 9? Yeah. Well, is it 0.98?
I misspelled chicken. I misspelled that. I misspelled
If we succeed 20% of the time. Yeah. Yeah. What's the likelihood? What does it mean to succeed? What is like a success? So whether we visit the doctor, what's the likelihood that a random person visits the doctor? 1 in 5. Yeah, exactly. Okay. Yep. And then we need to factor in the failures as well. So what's the likelihood of failure? So if we're succeeding 20% of the time, we're going to fail 80%. And how many times do we fail? Yep. So if we're seeing 3 successes in our sample, how many failures? Out of 10. So we would expect to see 7. Perfect. Okay, so what did it mean to get a success here? What is quote unquote a success? Yeah. What does a successful trial look like here? So picking a random person and that person having seen the doctor. Okay. So technically speaking, the trial is like the picking the person part. And the likelihood of success is the likelihood that they have in fact seen the doctor, which is, you could write this as either 1 in 5 or 0.2, whatever, 20, however you want to communicate a 20% chance. If we have a 20% chance of success, what is our likelihood of failure? What's our chance of failure? That's an 80% chance of failure, 0.8 or 4 out of 5. Either way is fine. And so what is the probability that I see 3 successes here? How many ways am I going to be able to pick 3 successes out of 10? 10 choose 3. Okay. What is we said likelihood for success? And how many times is that going to happen? 3 times. And then what is my likelihood for failure? 80%. And how many times is that going to happen? 7 times. Okay. Plug it into your calculator. This works out to be exactly what we see here, which is 0.201. So about 20% of the time we would expect to see this. One more example. Let's take a look here. In this case, we are trying to figure out the probability that our random variable is at least 3. So at least means that we would be happy if it's equal to. We'd also be happy if it is greater than. So greater than or equal to 3. If we're selecting from 5 and we want to see at least 3 successes, what are our options for what our random variable could be that would give us at least 3 successes? 3, 4, and 5. So it's either that our random variable is 3, or that our random variable is 4, or that our random variable is 5. Okay. If I have the probability of a bunch of OR statements, what do I have to do? Add them together. Normally when we add them, we also have to remember to subtract the overlap. Are we ever going to have a sample of 5 people that have exactly 3 successes and also exactly 4 successes? No. These are, what's the word? Mutually exclusive. Very good. And so because they are mutually exclusive, this should just be the sum of all of each of these individual probabilities. Also, please note, when I am referring to these events as being successes and failures, I am not condoning driving without a seatbelt. That is not a value statement. That is an experimental statement of, is the person that we are looking at meeting the criteria that we are defining? This is not an endorsement. Drive responsibly. Okay, what's the likelihood of getting 3 successes? How do we do this? So for probability of x equals 3, this is going to be, how many do we want to pick?
3.
Other way. 5, choose 3. Yep. And then what's the likelihood of success? Yep, to the power of 3. Yeah. And then likelihood of failure? Yep, 2 failures. Who are driving responsibly, which is good. We laud them for that. Likelihood of getting 4 successes? Try it 5, choose 4, and then likelihood of success, which should happen 4 times, and then failure would be once, which is likelihood of 0.7. Okay. And then lastly, getting 5. 5, choose 5, which is really just the same as what? Just 1. But I'll have it here just so we can see the pattern. Likelihood of success, we said 30%, which is going to happen 5 times, and then likelihood of failure 0.7, which is going to happen 0 times. Yeah. What is 0.7 to the power of 0? Not 0, 1. So the fact that 5 choose 5 is there, the fact that the 0.7 to the power of 0 is there, mostly just there to show kind of the pattern continuing. But it does hold. And so adding all those together. All right. Quick pit stop. Well, first of all, any questions with what we're seeing here? I forgot to do this with my 4th period. I'm probably going to forget again tomorrow. Oh, well, sucks for them. Quick pit stop before we move on. I do want to display something. So it's not too bad to do this by hand. And I think a lot of the pieces make fairly intuitive sense, like where the probabilities are coming from, all the combination stuff. The great news for us, though, is that our calculator will do this for us.
For all of it, or just
all of this? Yeah, calculator will do all of this for us.
No, I'm talking about like 5.1.
No, just for the 5.37.
Can we write it in this part right here? Or is it on the next one?
Well, no, this is like a continuation of what we're doing here. So like we're going to do the mean and standard deviation stuff. We'll have to do that on its own, but it's not too difficult. Okay, so in your guys' calculators, if you guys would go second, and then by the arrow keys, there's this vars button, pull up the distributions. We want the binomial PDF. In particular, this was a case where we wanted to have, let's say we had 5 different people that we were considering. We wanted, the probability of success was 30%, and we wanted to look at the likelihood of getting 3 successes. Second vars. Going down to binomial PDF.
Is it x to?
So we want the value of x to be 3. We want the probability, the p, to be 0.3. PDF? Yeah, PDF.
Yeah, but I know PDF.
Trials, we're doing 5 trials. Probability of success, 0.3. And then the number of successes, or x, should be 3. And when we do that, we find that our likelihood for having 3 people out of 5 who don't wear a seatbelt is 13%-ish. And we could combine that with the likelihood of getting 4 people who meet that criteria and combine that with the likelihood of getting 5 people who meet that criteria. And so ultimately what we would see is 0.163 as this probability. But this is how you would do this in your calculator with this binomial PDF. Yeah, it's not too bad by hand, is the other thing. Yeah, so don't worry about this too much. I just wanted to show you that it can be done. If it feels comfortable by hand, then it doesn't take too long to do it by hand. So. All right. So we have seen, vis-a-vis the bell work, that we can just go about calculating the standard deviation and the mean and the variance like normal, right? We could do that. We certainly could do that. One of the benefits, though, of working with a very specific distribution is that we can often take shortcuts when it comes to figuring out things like mean and standard deviation and whatnot. Often those formulas become a lot more specific. And that is certainly the case with what we are going to see for our binomial distribution. And we can kind of come to a lot of these conclusions just based on our intuition of like what expected value should mean. So for instance, if I have a coin, and we'll say 50% chance of heads, 50% chance of tails, and I flip my coin 10 times, what would my expected value for heads be? So the likelihood of heads is 50-50. So if I flip my coin 10 times, what value would we expect to see?
5.
We'd expect to see 5. How'd you do that? Yeah, this is just 0.5, the likelihood of success times the number of trials. So if I flipped my coin 50 times, what would my expected value be? What would my likelihood of success be? Which is 25. We'd expect half of the coins to become heads. So if, again, looking at the expected value after 50 flips would be 25. And this is going to be true for every binomial setup. It doesn't matter what the probability is. If we want to find the expected value, which expected value is just a fancy word for what? The mean. That's just the same thing as mu. Well, all we need to do is take the number of trials times the likelihood of success. If we succeed 60% of the time, then 60% of however many trials we're taking should give us success. You can see that in the bell work. That's exactly what we got, right? We said that our expected value was 2. Well, 50% of the time we're getting heads, and 50% of our 4 coin flips work out to be 2 heads. Sure. We also have abridged versions of variance and standard deviation. So for instance, if we want to figure out variance, which we did by hand, and the way we did it by hand was totally fine. But if we want to modify, make it maybe a little bit easier on ourselves, then for specifically the binomial distribution, this is going to be mu times 1 minus p. Well, this is for variance, and then we'll take the square root for standard deviation.
So yeah.
Yeah. Or you can write this as n times p times 1 minus p or times q, which are the same thing. Which again, notice our mu over there was, we said 2, and then, or rather, yeah, mu was 2, and then probability of failure was 50%. Variance works out to be 1, right? 2 times 50% is 1. And then how do I go from variance to standard deviation? Take the square root, so the square root of mu times 1 minus p. This is just like a shortcut way to do things. Again, we totally could do the same thing that we just did. The only annoying thing with that is we would need to have the entire PDF. And for 9 coin flips, that's already a really large sample space. For context, for 9 coin flips, we're looking at 512 different possibilities, which would be annoying in order to kind of parse through. And we have ways to parse through that, but we're not going to worry about unpackaging that. Okay, so let's take a look at the back here. We are told that a die is rolled 360 times. We are trying to find the mean, variance, and standard deviation for the number of 4s that will be rolled. Okay. So what is our probability of success and what is our probability of failure? If I roll a die and I look down at it, what would I need to see in order to count it as a success? I need to see a 4. How often is that going to happen? 1 out of 6 times? So if I'm succeeding 1 in 6 times, how many times am I going to fail? 5 out of 6 times. Perfect. Okay. What is my, if I succeed 1 in 6 times, what is my expected value or my mu for successes? So what do we do here to find expected value? So we're doing 360 trials, 360 dice rolls. We expect to succeed about 1/6 of the time on average. So how many successes would we expect to see? 60. 360 times a 1 in 6 chance of success gives us an expected value of 60 successes. Okay. How do I then find my variance? What do I do with that mu? Is it m times p? M times... Okay, you knew np times q. That works. That's fine. But we could also do mu times q, or mu times 1 minus p, which is 60 times 5/6. or 50? And then how do I find my standard deviation? Probability of failure. Probability of success is 1/6, which is already built into the 60. Yeah. We take the square root of it, exactly. So take the square root of 50. This works out to be about 7.07, which again, we don't have context for what that means. For our intents and purposes, that just means like we just have the notion of if it's big, then the data is really spread apart, and if it's small, then it's not as spread apart. We don't know if this is like particularly big or particularly small or what have you. Who knows? Questions with our mean, variance, standard deviation for the binomial PDF specific? Feel okay? Okay, take a stab at the final example here with the twins.
And we're gonna find all three of these.
Yeah, looking for a mean. Ultimately, the one that we care most about is standard deviation, but we have to get through variance to get to standard deviation. So go ahead and list that variance. That looks great. That's perfect. Looks good, Mark. What is the likelihood for success? It's 2%. So 2% of the time we succeed, then how often do we fail? A lot. Yeah, but we figure out the square variance. Why did you do the X40 out of the square root? I mean, this works. Okay, I mean, this totally works. You also just leave it as like 2%. And then is it 800? But otherwise, it totally works. I'm just essentially you made the traction more complicated, which is fine. It still works. It's still you just need
A 9? 16.
That's great.
Think about
Very
it.
nice. That looks great. Very, very nice. Looks perfect so far. What's our likelihood of success? So likelihood of failure. Looks great. Next question.
Copy me.
Okay, let's take a look at what we've got. What is our probability of success? 0.02. You also do 2 out of 100. I had someone in my fourth period ask why I use decimals sometimes and why I use fractions other times. I generally will use decimals unless I am not able to represent the fraction as a decimal, but either way is totally fine. If you did 2 out of 100 here, or 1 out of 50, or 0.02, that's totally fine. It's just for like 1 out of 6, it's 0.16 repeating, and I can't write 0.16 repeating in my calculator, so that's fine. And then what's the probability of failure? 98% or 0.98. Fantastic. So what is our expected value? What's our mu? 8,000 times 0.02, which is equal to 160. 160. What do I do to find my variance? Failure rate, which works out to be 156.8. And then what do I do with my variance to get to standard deviation? Take the square root, which works out to be 12.52. Which again, we don't have the context for what that means, but sure. Just tells us something about the spread. We'll interpret this a little bit more later when we incorporate z-scores. All right, questions with our binomial PDF? All right, so we have quiz on Thursday over 5153, which will be the last assessment for the quarter. Yeah, 51 through 53. So 51, 52, 53. Classworks 51 through 53 should be open. Got about 20 minutes left. You guys are more than welcome to spend the rest of this time working on Classworks. If you have questions that you would like to go over, more than happy to take a look at those. Whatever you need.
Okay.